Okay. All right, so here's the continuity equation again. So yeah, like I said, we're going to talk about the continuity equation for this class. And we're talking about this analogy. Before we get into the continuity equation, we're talking about this bucket of water analogy. So what we just talked about is that, there's a level of the water in the bucket, and that level changes over time depending on the rate in and the rate out. And we have four processes that are going on here. There's a pipe going in, so that's putting water into the bucket. Water can also condense if the bucket is in open air, so that adds water to the bucket. And the two processes that remove water from the bucket is that you have a pipe here that's pumping water out, and you may have some evaporation too that also removes water from there. And the units for each one of these processes is liters per second if we're using the MKS system. All right, so if we look at these all in an equation, the rate in, so the things that are contributing, that are increasing the level of water in the bucket have positive signs associated with it. So R in, so the pipe going in is putting in water at a certain number of liters per second. Then you have this condensation rate that's also putting in water at a certain rate, liters per second. And then you have the negative processes that are taking water out of the bucket, and those have a negative sign associated with them. So rate out is the pipe, and then the rate of evaporation. So you have these four processes, and if those four processes all add up to 0, then the level of water in the bucket doesn't change. Okay, that would be a steady state situation. The way that we define steady state is when all the time derivatives go to 0. So this is a time derivative, dw dt. So in steady state, all time derivatives go to 0. So if this goes to 0, then that would be a situation where in steady state, all of these four processes have to be balanced with each other. They have to add up to 0. Okay, so this is a statement of conservation of mass. So the mass, that you can think about that as a conservation of the water molecules. Okay, and now with the electronics analogy, it's a statement of conservation of charge. There are certain processes that create charge. There's certain processes that destroy charge. There's certain processes that cause charge to flow into an area, and there's certain processes that cause charge to be removed from an area. Okay, so that's the reason why the continuity equation is important. It's a basic statement of conservation of charge, and all the processes that we learned about in this module so far, diffusion, drift, generation, recombination, they all are processes that contribute to charge movement or charge generation and charge removal. So they all kind of go into this equation. All right. But the basic statement is conservation of charge, just like the previous one was conservation of water. So let's look at what's happening here. What we're doing is we are taking a block of material, electronic material, okay, and that's shown in gray, this gray box here. And think about this as your bucket, okay? The charge can be pushed into that bucket, so you could have a process that puts charge into this region. You could also have a process that removes charge from this region. So when we're talking about charge in, we're talking about charges flowing in. Just like water flows in like through a pipe, this is where charges flow into the material from the left side here. And there can also be a process where the charge flows out of the right side. Okay, that's the analogy of the two pipes going in, a pipe in and then a pipe out. Then there's also the processes analogous to evaporation or condensation, where you're generating charge or destroying charge. And what are the two processes that we talked about in class that correspond to those two?
Generation and recombination.
Generation and recombination, that's right. So the flow of charge inward is adding to charge in the material, and then generation processes are also adding charge to this gray region. The flow of charge out of this gray region is a rate out, and so is recombination, because recombination is also removing charge. So the way that we define this region is we say the beginning of this region starts at location X, and the end of the region is X plus delta X. So just a small region of the semiconductor. This delta X, we're going to make it very, very small. So in this area, we have a current flowing in and a current flowing out. So the current flowing in, the charge in is Jp of X, and the charge out is Jp of X plus delta X. Okay, let's think about units here for a second. So with the water, in the case of water, we were thinking about flowing water into a bucket. So the units was liters per second. What would be the units in this case? Coulombs per second, right? Coulomb is a unit of charge. So we're dumping charge into that material. So that's coulombs per second. So there's coulombs per second going in here. There's coulombs per second going out here. So this is denoted Jp of X, and the charge out is denoted Jp of X plus delta X. So that is the current on the right side of the gray zone. Okay. I don't know if you think back to circuits 1, the Kirchhoff's current law says the charge going in, the current going into a resistor has to be equal to the current going out of the resistor, right? That's at steady state. Okay, so we're able to say here that this may or may not be equal to each other. So we're trying to be very general here. We're not trying to put any constraints on it yet. All right. So similarly to what we did with the bucket of water analogy, with the water we were saying the rate of change of water in the bucket, dW dt, in liters per second. Here we're saying the rate of increase in charge in this volume, and so the units here is going to be coulombs per second. So if dP dt happens to be positive, that means we're building up charge in that little region, okay? And if dP dt is negative, that means we're losing charge in that region, okay? So the rate of change of charge in the region is equal to the rates in and minus the rates out. So the processes of the rate in process is the current going in. So that's R in. And then the other process that's positive is the generation rate. So there's a rate of generation here. The two negative processes that's removing charge from the material is this R out. So that's the current out, the Jp of X plus delta X. And then there's also a recombination process. It also has a negative sign associated with it. So now we take our understanding of those four processes that we talked about earlier, and we plug those into this equation. So the rate in minus the rate out, it turns out that the rate in, we already know how to calculate current going in. There's the diffusion and drift processes, but we're not even getting into that yet, okay? So this formula is not coming from diffusion or drift. We're just stating, we're making a statement that this is Jp of X going in here. Okay. So this is a current density. The units for this is given in what's the units for current density? Let me ask you that. Amps per centimeter squared, exactly. So the units for Jp of X is amps per centimeter squared. Okay? Now we're taking the rate out. This is Jp of X plus delta X. The units for this is also amps per centimeter squared. Okay, we're taking the difference of the two. And we have to divide by this delta X to get the correct units. Okay, because this is amps per centimeter squared. This is amps per centimeter squared. And divide by, if you divide by delta X, what are the units that you get? amps per centimeter cubed. Amps per centimeter cubed, because that's the charge in the volume. You know, we're talking about this volume, okay? Now, when we take that and we divide by Q, what are the units we're getting here?
1 over centimeter cubed.
1 over, yeah, this is, no. This is amps per centimeter cubed. Okay, an amp is a coulomb per second.
Amps again by coulometer.
Let's write this down and make sure we all understand. So this is amps per centimeter squared. Right. So this is equal to coulombs per second per centimeter squared. The second term here also has the same units. Okay. This has units of centimeters. All right. So you take amps, coulombs per second per centimeter squared. You divide by centimeters. So this whole thing here has a unit of coulombs per second per centimeter cubed. And then you divide by Q. What's the units for Q? It's 1 over coulombs, right? So for this entire thing, actually, let me draw that in a different color just to be clear. I'll draw it in green. So the units for this entire thing is going to be amps, sorry. So it'll be coulombs per second per centimeter squared. And then you also have the 1 over Q term, which is 1 over coulombs. And then you also have this 1 over centimeter term. All right, so you're going to be left with 1 over seconds per centimeter cubed. All right, so that's the units for rate in, rate out. It's actually the units for all of these guys. Okay, so the unit, 1 over. So this is the amount of charge per second per centimeter cubed. Okay, so it looks like there's actually an error here. This should not be coulombs per second. Okay, let's fix this here. This should also be, so charge per second per centimeter cubed. Okay, because we're considering the volume of this area. Okay, so this 1 over second might be a little bit confusing, but that's because it's talking about the number of charges per second. Okay, it's not talking about charge of coulombs. It's talking about the number. You could talk about the number of carriers per second per centimeter cubed. Does that make sense? It's better if you think about number of carriers per second per centimeter cubed. Okay, good. Cleared that up. So these processes are also going to be similar. The recombination process is equal to sigma p over tau p. This is the definition of the recombination rate. And the units for this also is 1 over seconds per centimeter cubed. Okay, so this is the excess carrier concentration, the excess hole concentration divided by the carrier lifetime for holes. Notice that in this example, we are just talking about holes. Okay, we talked about Jp of x, Jp of x plus delta x, and we're talking about sigma p divided by tau p. We're just doing holes right now, but the same exact thing will apply to electrons as well. Okay, so that's, we're just picking holes arbitrarily. So this is the recombination rate. It's the excess hole concentration divided by the whole carrier lifetime. So again, that has units, same thing, because like the excess carrier concentration has units 1 over centimeter cubed, and the carrier lifetime is 1 over seconds. So that also plays in. And then we have the generation rate here. Okay, the reason I didn't have a formula for that is we're actually just going to ignore generation in the next slide, as we'll see. Okay, so this is a statement of we're conserving the charge that goes in and goes out, generated and recombinated. So now we're going to solve this one. So this is the same equation that was on the previous slide. And what we're doing here is we are just going to assume that there's no generation, just for the time being. Okay. Because you have some stuff that's flowing in, stuff that's flowing out. The recombination can happen if you have excess carriers in this region. All right, but we're not shining light on the material, so there's no generation happening. So this is the key part of the equation that allows us to come to a differential equation. This difference in current, so there's the current going in and then the current going out. So the current going in is Jp of x, the current going out is Jp of x plus delta x. And you notice how we divided by the delta x here. This term here looks very much like a derivative term in mathematics. You take the difference in functions in one position versus the next. So let's say the current is a function. There's a current at position x. There's a current at position x plus delta x. And then you divide by delta x. If you go back to your mathematics books, that's like the definition of a derivative. If you take the limit as x goes to 0. So you take the limit as, you make delta x go to 0, and then this whole thing becomes a derivative. So that's the reason why we wrote the equation this way in the first place. Okay, the intuition is this, is that the difference in current going in versus going out is basically going to be the derivative of the current with respect to space. All right, so this becomes dj dx, the derivative of current with respect to x. And nothing happened here. This recombination term just came down here. This also stayed the same. The notation, this should also be d, if we're talking about excess carrier concentration, d sigma p dt. All right, let's go back to red. I think that's easier to see. All right, everyone with me so far? Okay. The next step, then we plug in the formula for the diffusion current, Jp. So this current, Jp, we're going to assume for a second that it's just due to diffusion, because there's no voltage being applied to this thing. So it's just due to diffusion. So if you don't have voltage, then you don't have any drift currents. So the only way that you can get a current in the semiconductor is by diffusion. So we are assuming that Jp is diffusion. Diffusion current. All right, and this is the equation for diffusion current that we talked about. Oops. This is the equation for diffusion current. So that's I mentioned this in class last time. Negative Q times the diffusion coefficient times the gradient, the carrier concentration gradient. All right. So notice that this equation for diffusion current has a derivative in it already. is d sigma p of x dx. So there's a derivative here. And when you plug this in, you're asked to take the derivative again here. So the equation that you get here is a second derivative. Okay, we first came up with this equation here, djp dx, but we found, remember that jp itself is a derivative of carrier concentration. So this equation then becomes a second derivative of carrier concentration, d squared sigma p over dx squared. And then this term just came down as usual. All right, so the assumptions that we made here, there's no light being shined on the material, there's no generation, and also there's no voltage being applied to the material, so there's no drift current, there's only diffusion current. Under those assumptions, we come up with this equation here. So this example is the continuity equation being applied to holes. Same derivation applies to electrons, almost the exact same thing. All right, any questions? Yeah.
So what is the purpose of assuming no generation here? Because that is not affecting any of the form.
Yeah, I mean, if you assume that there was generation, then the generation term would just show up here in the differential equation. That's right. We're just simplifying it for the types of problems that we're going to be looking at. But it turns out that this. I'll get to that in a second. This is the continuity equation in the general case and then in the steady state case. So we just took this result here that we got. Okay, copied it over here. So this is the continuity equation in the general case where carrier concentrations change with time. So this is the recombination process that's happening. This is the this process is the difference in current in versus current out. And then this is the rate of change in carrier concentration versus time. Okay, and this is the same equation for the electrons. Now, if you do have a generation process that's also there, then you would want to add that term in there. Yeah, but as you're going to see for the examples that we do later, we're calculating carrier concentrations in the region without the light on it. You'll see in the next example. Okay, now this is a general case, but in steady state, remember that the time derivatives, this time derivative and this time derivative go to zero. So under steady state conditions, these are the continuity equations. So this term goes away. So d sigma p dt, the left side goes to zero. And so then this term has to equal this term. And so that's what we have here. D squared sigma p over dx squared is equal to sigma p divided by dp times tau p. So you see how the tau p is here and the dp is here. So when you move that over to the other side, that's where these two terms come from. So this product turns out to be pretty important. Turns out to be physically relevant. So dp is the diffusion coefficient, and then tau p is the carrier lifetime. Okay, the product of those two is the, and if you take the product of the two and you take the square root of it, we define that as the diffusion length. Okay, this will make sense when we talk about the next problem. But what the diffusion length is, you can think about it intuitively, is the average distance a carrier diffuses before it recombines. Let me fix this. The average distance a carrier diffuses, I want to be more specific here, before it recombines. Average distance a carrier diffuses before it recombines. Okay, so this triple equal sign is it's a definition. So we are defining the square root of dp times tau p as LP. So this equation then becomes, this right side of the equation becomes sigma p divided by LP squared. And similarly, sigma n over ln squared. All right. So you may be wondering, like, why do we arbitrarily, like, just define this diffusion length term, this LP term? How does it physically make sense? And it'll make sense. It'll make sense on this next example that we'll see here of localized injection. But let's just, before we get to that, let's just remind ourselves what these equations are. These are differential equations, and you notice that the differential equations are a function of x. Okay, so these equations are describing carrier concentrations as a function of location. That's what the steady state equation is doing. In the general case, what is it a function of? It's a function of space and time, both. Right? So the general case is the general equation are the ones that you start off with, but if you have a specific situation like steady state where all the time derivatives are zero, then the equation just becomes a function of space instead of space and time. All right, so we're looking at some examples of steady state. This is where we'll look at an example of that. We also looked at examples, time-varying examples where there wasn't, we weren't concerned with the spatial portion of it. So most of the examples that we do in this class, the equations become a function of time or they become a function of distance. It is possible to have ones where there's both. Those problems are a little bit more tricky to do. So let's do an example of steady state continuity equation. All right, and so here's the continuity equation example. This is what's called localized injection. So injection, the term injection, by the way, is you can think about getting an injection like where you're injecting something into your blood. We are injecting carriers into a semiconductor. And the way that we're injecting the carriers in this particular example is with light. Okay, we're just generating those carriers. So they sometimes refer to that as injection. So the problem looks like this. Suppose carriers are injected at x is less than 0. All right, so it's going to be on the left side. What is the diffusion current? So we have light illuminating the left side of the semiconductor block, and the right side is left in the dark. So before we start doing the calculations of this, I want you to think about, in terms of the 4 carrier processes, which one of those 4 processes, not one, which of those carrier processes will occur? Because this is a great example to really think about that. Let's start at the beginning. Let's start. The first process that we know of is generation. Generation is happening. Why? Let's explain. Let's make sure that we're all on the same page. Why is generation happening?
So light is exposed.
Light is exposed, right?
So the carriers.
Yep. So we are generating carriers on this side of the material. Okay. How about the right side? Are we generating carriers on the right side of the material?
Diffusion.
Yeah. We'll get to the diffusion part of it, right? That's but there's no generation happening because there's no light being shined on the material. The next process, diffusion, right? So diffusion is happening on the right side of the material because we are creating a whole bunch of carriers here. So there's excess carrier concentration here. So there's a high concentration of carriers on this side, lower concentration of carriers on this side. So you think about this, you're generating electrons and holes here, right? And those excess electrons and holes are going to want to diffuse over to the other side. So they're all going to want to go this way, right? They diffuse from high to low concentration. We'll get into the equation on the next slide. I wanted to just focus on the qualitative concepts here because I think that's important. So on the left side, we're generating these excess carriers, and on the right side, there's no those excess carriers don't exist. So at the interface between the two, if we want to be very very specific about it, we can say that at the interface between the two, there's diffusion happening. Right. So way out here, there may not be any diffusion, but close to the interface, there's going to be diffusion. Right, because there's a concentration gradient here. All right, how about drift? Is there going to be drift? Why is there not going to be any drift in this problem? There's no voltage applied, no electric field, correct. All right, how about recombination?
Yeah.
Why will there be recombination? And well, let's start with the left side. Is there recombination on the left side?
Yeah.
There actually is. There actually is recombination on the left side, but let's think about why. What determines the recombination rate? I just want to hammer the concepts over and over again.
Generation?
Generation has to do with it, but what physically, like what does recombination mean?
Electron hole pairs.
Electron sees another hole, they recombine, right? So what's going to impact recombination?
Higher concentration.
Carrier concentration, right? So the fact that we have excess carrier concentration means that there's going to be more recombination. We shine light on the material, it increases the generation rate, and it also increases the recombination rate. Both. And they're both in equilibrium. These equations that I showed you earlier, like steady state carrier generation, these apply to equilibrium when the generation and recombination processes are balanced with each other.
Well, Professor?
Yeah.
Technically, doesn't it take a second to get to equilibrium?
It does, but the equilibrium, when you shine light on the material, the equilibrium is established very, very rapidly.
Okay.
Yeah. So that's why we almost we sort of ignore that. But that's a very good point that you brought up.
Okay.
It does take a very, very small amount of time for that equilibrium to be established. But it turns out that when you turn the light off, then it takes longer times for those carriers to decay away. It's a subtle but important point. When you turn the light on, that equilibrium is established very rapidly. Generation, recombination, they establish a very quick equilibrium. So the carrier concentration, excess carrier concentration goes up almost immediately. But when you turn the light off, now you have that concept of the minority carrier lifetime, where there's an exponential decay over time. It takes a little bit of time for those carriers to die out. And the carrier lifetimes are typically on the order of like femtoseconds to picoseconds, sometimes nanoseconds or microseconds. There's a big range in which they can occur. But the process of the light turning on and creating the excess carriers, that happens much faster than the carrier lifetimes. Good question. All right, so recombination is happening on the left side. Is recombination happening on the right side?
Yeah, close to the concentrated gradient or whatever.
Exactly. Great point. Why is there more recombination near the interface?
Because electrons and holes, they're only going to go so far because you only have the light shining on the left hand side.
Exactly. Light shining on the left side, so you're injecting carriers onto the right side. That's why they call this localized injection. And so the excess carriers that are diffusing over to the right side, there's a higher carrier concentration at this interface, right? So there's going to be recombination there. The way that you can think about this is that the carriers are generated on this side, then they diffuse over to this side, and then they recombine. Okay, so there is going to be more recombination out here. And one more question I would ask you. This is a bit of a trick question, but is there recombination out here?
Depends how much energy is applied.
Depends how much energy is applied. Yeah, that's true. Mm-hmm. But what if there's no light applied at all?
Oh, nothing's gonna happen.
That's the trick question I'm actually getting at. If there's no light on the material at all, is there recombination?
No light, no.
Well, let me ask you another question. If there's no light in the material, is there generation? I think before module 4. It turns out there is the only way to turn generation off completely is if you go to absolute zero. So at room temperature, there's still some generation processes happening, but it's extremely small. It's small, it's negligible, but it's still happening, right? So if we, that's why it's a bit of a trick question. The only way we can turn off generation processes completely is to go to absolute zero. Because remember our band gap, like there's a certain amount of energy, electron at non-zero temperatures, a very small probability of electrons can actually jump up into the conduction band. That's generation. So yes, there is generation processes, and therefore there is recombination processes also, because they're happening in equilibrium. But the generation and recombination processes are much higher on the side with light. And there's no generation, there's minimal generation happening on the right side of the semiconductor, but there's a lot of injection happening. You're injecting all these excess carriers, and because the carrier concentrations are larger due to this excess injection, there's going to be more recombination happening here. All right, so think about a carrier being generated on the left side, and then they diffuse over to the right, and but within a fraction of a time, within a very small amount of time, they recombine. So this gets us now to our definition of diffusion length. So the definition of diffusion length was that diffusion length is the average distance a carrier diffuses before it recombines. All right, now in this example, you should see exactly what that means. You're generating carriers on this side, they're diffusing over to the right side, and then they're recombining. So the diffusion length is the average distance that this carrier diffuses over to the right side before it recombines. All right, so let's say the diffusion length is something like this, LP. It could also be LN. And then once, by the time you get past the diffusion length, most of the carriers have recombined. Okay, so any questions on this so far? Very important, this is a good example to understand the 4 carrier processes.
What does most recombining mean, like 90%, 50% at that diffusion length?
It's 1 over E. So 70% of them have recombined.
Okay.
Yeah, 1 over E. Because it's an exponential decay process. Okay. So we're going to get a little bit more quantitative with this now. So I have the same example here, but we're going to solve the continuity equation for this example here. We're shining light on the left side. Electrons and holes are being generated. They're diffusing over to the right. So you start with the steady state continuity equation at x is greater than 0. All right. Remember, we're starting with the steady state version, not the time dependent version, because what we're doing is we're going to shine light on the material and we're going to keep that light on. We're not turning it off so that the whole system is in steady state. If we were flickering the light, turning the light on and off, then we'd be in a different situation. Okay, this is steady state continuity, a steady state light source. So this is the equation that applies. We're only solving this for holes, mind you. We're only solving it for holes, but the similar derivation would apply to electrons as well. So the first step is that you solve the differential equation to find the carrier concentration profile. This is a form of differential equation that is well known. When we talked about Schrodinger equation, I said you don't need to know how to solve differential equations. Just understand that there is a solution to it. So the solution to this type of differential equation, the second derivative, is equal to the function itself, function of the function itself. The solution to those types of differential equations come in the form of an exponential. Okay, the equation form looks like this. So, in this differential equation, the unknown was this function, sigma p of x. That's what we want to find. What we're trying to find here is we're trying to find what does the carrier concentration profile look like at x is greater than 0. I should have mentioned that at the beginning of this. What are we trying to solve? What are we actually trying to find? We are trying to find an equation that describes the carrier concentrations at x is greater than 0. Okay, so the steady state continuity equation can apply on this side, on the right side of the semiconductor, because there's no generation term in there. There's no light, so there's no generation term. That's getting back to the question that you mentioned. We're not solving the continuity equation on the left side. We're only doing it on the right side, where there's only recombination happening. So the sigma p e to the negative x over lp. Notice that, and this gets back to David's question, like, what is the significance of this lp term? You notice how this is the denominator of the exponential? So when x is equal to lp, then this term is going to be equal to e to the negative 1, or 1 over e. So by the time you go a distance lp away, it turns out that the carrier concentrations have gone down to 1 over e, gone down by a factor of 1 over e. Does that make sense?
Yeah.
Okay. You'll have a problem like this in your homework, so that'll hopefully clear it up. So the form of this equation looks like this. It's sigma p e to the negative x over lp, and this is what the equation looks like. An exponential equation looks something like this, where this is x, and then the initial amount is the delta p that you see here. That's the delta p here, and it's an inverse exponential function that looks like this. And the rate is determined by rate of decay determined by the diffusion length, L sub p. If L sub p is large, then the decay rate is very, very low. If L sub p is small, the diffusion length is small, that means it's a very rapid decay. So from here, we can calculate the current from the carrier concentration profile. So we're not only interested in finding the carrier concentration, but we're also interested in finding the diffusion current, because the diffusion current is something that we can actually measure. So what we would do in the actual experiment is we'd shine light on the material here. We looked, and we could actually measure the amount of diffusion current that's going over. We can do that with an ammeter. The way that we do that is the diffusion current, Jp of x, equal to this. This is the definition of diffusion current for holes, Q times dp dx. Right, we saw this earlier. And plug this into the equation. So we have an equation for sigma p of x. So we take the derivative of that here, and then we come up with this equation here. So remember, this is this equation, dp of x, sigma p of x, is an exponential function. The derivative of an exponential function is an exponential function. Right? So all we're doing here is we are taking the derivative of this function up here. Okay. If it's not obvious, this should be d sigma p of x, not dp of x. Just a correction there. All right. So you take the derivative of this exponential function. The LP term comes out in front, and that's where you get dp over lp, and then you have the exponential function again. All right, so all we did is we took the derivative of this function and multiplied it by the diffusion coefficient. These are what the actual results look like. So this is a plot showing p of x, sigma p of x. This is the excess electron concentration. Oh, no, I'm sorry. This is actually showing P of X. My bad. Notice that this is decaying down to P0. I see some puzzled looks. So just remind everyone that P0 is the holes due to doping. So this is before we shine light on the material. Without light, this is what the hole concentration would be. Sigma P is the excess hole concentration due to, what is the sigma P due to?
Generation.
Yep, due to generation, so it's due to the light. Yep. And so the total P is equal to P0 plus sigma P. So this is the total hole concentration. All right, so when we're showing P of X here, this P of X is the total hole concentration. And what's being plotted here is it being plotted against X. So at X equals 0, there's a high level of holes, and as you go further along, the number of excess holes goes to 0, and so this function, the total hole concentration, it drops down from it drops down to P0.
Does it actually go to P0? Because that line might be a little misleading there.
This line here,
Yeah, does that actually touch P0?
it exponentially asymptotes to it. You know, it's an exponential decay. So essentially it'll go down to P0. But, you know, if you're really mathematically particular, it's not going to ever be totally equal to it. Yeah, so that's a good point. But it decays down quite rapidly because it's just an exponential decay. All right, and this is the region where diffusion is happening. So wherever you see a gradient in carrier concentration like this, right, it makes sense. The carrier concentration is high on the left side. So on the left side, if you were to continue the function here, drawing the function, it would look like this. It's like flat like this, and then right when you get to x equals 0, it starts to drop off. This delta P can be calculated with the equations that we saw earlier in last class. Sigma P is equal to tau P times GOP. This is a steady state light source. So this generates a certain excess carrier concentration. So that's what this is equal to. GOP times tau P. And then right when you get to x equals 0, there's an exponential decay with respect to x. Okay, and that's what this equation is basically showing. All right, so there's a high concentration on the left side, and then the carrier concentration decays down like this. Now, if you think about, there's two things I want to point out here. Whenever you have a concentration gradient like this, that tells you that there's a diffusion current, because diffusion currents are driven by concentration gradients. All right, so if I showed you this plot and said, like, is there going to be a diffusion current? The answer should be yes. Another way you can kind of look at this plot is that there's a high concentration of electrons on the left, but as the electrons are diffusing to the right, they're recombining. Some of them recombine quickly, and some of them take a long time to recombine. These are all statistical processes. It's not that every single hole and every single electron diffuses the exact same distance before it recombines. It's stochastic. Some some recombine quickly and some take a little bit longer. That's why that term, the carrier lifetime, or the carrier lifetime, is the average time that it takes for a carrier to recombine. And then the diffusion length is the average time it takes for, the diffusion length is the average distance a carrier travels before it recombines in this type of situation. All right. Does that make sense? So some electron as the whole is diffusing over. Oh, this one happens to see an electron, so it diffuses, it recombines right away. Another hole takes longer, right? Let's say that hole is picky, so then it ends up finding its electron a little bit later, and so on.
It depends to their age.
It
depends to their age, their lifetime.
Yeah, exactly. The diffusion length is actually quite very related to the lifetime. Let's look at the definition for diffusion length. It's proportional to the square root of the lifetime. So, however long, if it takes longer for it to recombine, it will diffuse longer during that time. Good. All good questions. So this is basically all the points we were talking about. Okay, so we talked about localized injection, and now we can talk about the one more topic that I added to the grad class, because I think that it's interesting and it's also very practical. So the question is, the utility of this method, the Hanes-Shockley experiment, is it's used to measure the mobility mu and the diffusion coefficient of a semiconductor. All right, we know that we know so far that those two parameters are super important. All right, the mobility determines how fast an electron moves, when you apply an electric field to it. So the resistivity of the material is going to be determined by this mobility, and the diffusion coefficient determines how fast things diffuse. And the diffusion coefficient, as you know, it's proportional to the mobility constant. The first module in the class, remember I talked about that people are researching new types of materials like graphene and carbon nanotubes and low dimensional materials, high mobility materials. The mobility is one of the first constants that people are interested in when they're examining these new materials, especially these days, because high speed, everything is about high speed these days. High speed amplifiers, high speed computation, low resistance materials. Those are all desirable electrical properties. So being able to measure mu is fundamental. So this is one way of measuring the mobility is this Hanes-Shockley experiment. Another way I want to mention before I get into this, actually another way of measuring the mobility, if you're just interested in measuring mobility, is you could just do a basic resistance experiment. If you remember from the last module, we said the resistance is equal to, the R is equal, let me write this down. R equals L over sigma A. And then sigma, for an N-type semiconductor, it's Q mu N times N. All right, if it was a P-type semiconductor, it'd be Q mu P times P. So if you have a semiconductor in front of you and you know the doping, so if you know what N is, and you measure the resistance of a semiconductor block with known dimensions, so you know L, you know A, you can calculate sigma. So you measure the resistance with an ohm meter. You know what L and A are. You know what the dimensions are. And if you also know Q and N, so if you know what your doping levels are, Q is just a constant, then you can figure out your mobility that way. But this requires you to know the doping level. If you don't know the doping level, then you can use this Hanes-Shockley experiment. And the nice thing about the Hanes-Shockley experiment is also allows you to measure the diffusion coefficient D, both. All right, so let me just quickly explain like what this looks like. You put a voltmeter. I'm sorry, not a voltmeter. You put a voltage source across a bar of silicon. Okay, and then you create a flash of light on the silicon material. Okay, so you generate a narrow region of carriers with a pulse of light. So this slide shows what's going on here. So this is at time equals 0. So this is immediately after the pulse. T1 is a little bit of time later, and T2 is a little bit of time after that. What each of these plots is showing X is showing the position on the X-axis. On the Y-axis is showing the carrier concentration. So imagine this is the X-axis, and then the Y-axis that they're showing here is the hole concentration. If you create a flash of light in a very specific region like you see here, right, like they're generating this flash of light just in one portion. Let's say you started off by generating the flash of light just in the middle. So you generate all these carriers in the middle. Actually, no. Let's just do the example that they have here. So erase. So let's say that these were holes that you were generating. Okay, so it's well, I guess you're generating holes and electrons. This is an N-type silicon. You're generating holes and electrons. So there's some the holes and electrons are being generated. The holes are the minority carrier. So if this is what a carrier pulse would look like, because you're generating all these holes here, and so there's a high hole concentration wherever you put in that flash of light. But the thing you're also doing here, which is different than what we showed before in class, let me just back up here for a second. The beginning of the module, let's see, I showed this. Where was that example? Oh, here we go. Yeah. So just to remind everyone, like, we talked about this example. You generate a pulse of light right in the middle of the semiconductor, and you generate a whole bunch of carriers there, right? So they call it a pulse of carriers because there's a high concentration of carriers right where the light was, and then it decays down like this. All right. So when you have a profile that looks like this, what's going to happen here? The carriers, there's a sharp concentration gradient. Excess carrier concentration is high in the middle, and then it's basically 0 outside. So what process is going to happen here?
Diffusion.
Right, exactly. So the carriers diffuse out with time, and so this pulse of carriers, it actually widens out with time. Okay, so this was, in this experiment, we just had light. We had no voltage source. The Hanes-Shockley experiment is where we do a similar experiment, except this time we have, exactly. We put a voltage across it, so that pulse of carriers, it moves and it spreads out at the same time. So that's why the pulse looks like this initially. It's moving to the right because the way that we have the voltage set up here, the electric field is pointing from left to right, and let's just assume that these are holes. So the hole concentration, so this pulse of carriers is moving to the right over time, and as it's moving, the pulse is also widening out. That's what's happening. And so think about how fast that pulse is going to move. You generated carriers at one spot. The rate at which those carriers are going to move through the material depends on mobility. Right? Mobility is a constant that tells you, like, when you have an electric field, how fast do those carriers move across the material. Let's see. So the amount of time that it takes for this pulse to get to this side and be detected by the ammeter, that time can be used to measure mobility. And the width of the pulse. The width of the pulse gets wider and wider as over time. So when you get this pulse, when you read out this current pulse in your ammeter, it's going to have a certain width associated with it. It's going to be wide like this. And basically the way that this experiment works is that if you do the mathematics on this, then you'll see that this is an equation for the carrier pulse. It's equal to P max, so that's just the maximum hole concentration in the middle of the pulse, multiplied by this exponential, the exponential of x minus x max squared over 4 dp times t. So what this equation is actually saying, if you look up what the form of this equation, this is a Gaussian function. It's basically a bell curve. Right, and this delta x, this square root of 4 dp times t, this is the standard deviation of the Gaussian function. All right, so what you measure is that you get this current pulse on the outside, and you look at how wide that current pulse is, and then you can use this equation to figure out what dp is, what your diffusion coefficient is. All right, you have to know the length of the semiconductor and so forth to do that, because in order to be able to calculate how much time it took for that pulse to travel across. Okay, so the time for the carrier to travel, the pulse to travel across the silicon is determined by mu, and the width of the pulse is determined by d and also by mu. Okay, so this is a pretty elegant experiment that was done that basically incorporates all the 4 carrier processes that we talked about in this module, and they use it to measure the mobility. So in this experiment, like I think I've already answered my own question, but what are the carrier processes that are happening here? Is generation happening? Yes, we had a pulse of light. Is recombination happening? Yes, because you generated the pulse of light. Now, one thing, in order for this experiment to work, this is very important, is that the holes, what would happen if the holes recombined very quickly before they got a chance to get to the other side?
You couldn't take a time measurement?
It would be difficult. It would make things more difficult to be able to take that current measurement and measure the pulse. So this thing would die out very quickly.
What if you increase the voltage? Still down fast? Or?
If you increase the voltage, yeah, that would move the pulse quicker. So yeah, that's a good thought. So recombination processes are happening. Is drift happening?
Yeah.
Yes, because you have an electric field. Is diffusion happening?
Yes.
Yes, that's what's causing the pulse to widen out as it moves across. So all 4 carrier processes happen in this Haynes-Shockley experiment.
Do all the light should be focused just only on this area to the left, not on the whole?
Yeah, so what you're trying to do is you're trying to create a pulse of carriers so that you have this, so that you have a function that looks like this. If you shine light on the entire material, then you'd create light. You'd create carriers everywhere.
There's a black blocking thing with that one arrow on it.
Oh yeah. Thanks for That's an important point. Thank you for I figured.
Yeah.
That's notice that there's a small opening in the mask here. Thank you for making sure that everyone understands that. Yeah, I guess from this diagram it kind of looks like light is going everywhere, right? Yeah. Good point. By the way, does anyone know who Shockley was? He's all right. Well, you must know.
Did he invent a diode? Shockley. This is Shockley.
This guy, William Shockley, American physicist and inventor. He was he's credited with inventing the transistor. And
IBM Lab, right?
huh?
IBM Lab?
Bell Labs.
Yeah, Bell Lab, sorry.
There was a place called Bell Labs that doesn't exist anymore, unfortunately. But basically, all the brilliant minds, like in the 50s and 60s, they were all going to Bell Labs. It's like it was a time where industry funding for research was at an all-time high. These guys were like game changers. This guy is like accredited for creating the transistor, and all of the people who worked for him, they all ended up going out to start companies like Intel, Fairchild Semiconductor, like, you know, I forget what I forget what they were called, but I think he had 7 people working for him, and they were something 7. Let me see if I can look that up. It was like the it was a Traitorous 8. That's what he called it. I guess they were called the Traitorous 8 because they all left Shockley Semiconductor. Like, they were at Bell Labs, and then Shockley founded Shockley Semiconductor after the invention of the transistor, and then these guys all went out to found Fairchild, and then from Fairchild there's Gordon Moore and Andy Gordon Moore and another guy. They went. They said that.
There's their names here.
Oh, yeah, there you go. Gordon Moore and Robert Noyce. They went out to found Intel. So Shockley apparently was very like protective of all the experiments that he did. So he was kind of bonkers from one of the movies I watched about him. He received the Nobel Prize in Physics. He was credited for the invention of the transistor. But then, like, all the people that worked for him were also like super talented. So Shockley Semiconductor was the first company, and then Fairchild was one of the first companies doing, like, you know, they did a lot of like analog electronics, and then eventually they started getting into digital. They started doing digital logic gates, and some of that stuff was being done with bipolar junction transistors. And then Gordon Moore and Robert Noyce, they said CMOS is the way to go, where you have like MOSFETs, like N MOSFETs and P MOSFETs, and other people didn't believe that idea would work, so they went out and founded their own company in Intel, and it turns out that they were right in a big way, and Intel just kind of grew, just went bonkers from there. It's a really interesting history. Like, if you can look up movies on Netflix about this. There's a really good movie that I watched about the history of the transistor, and they talk about these guys, and it was actually very interesting. It was more a biography of the people than it was about just the technical stuff. So yeah, if I would highly suggest like just checking out the movie, because it's something that was a total game changer in how society operates. So it's interesting to see like how this group of people like totally changed the world.
Do you know what university these guys went to, or?
I don't off the top of my head, but you know, you can Wikipedia search it. Okay. All right. So to sum up this module, the carriers, we found that carriers can be created by several processes. You can create it by doping. The doping creates carriers of a single type. You can increase temperature. And when you increase temperatures, you generate electron hole pairs. In this module, we found if you shine light on the material, you can also generate electron hole pairs, but you can generate them very quickly. So you can apply transient stimuli to it, to a semiconductor. And then you can also do electronic injection. That's another way to create carriers. We actually saw an example of that here. We shined light on one side of the semiconductor, and then the excess carrier is diffused over to the other side. That's one way you're injecting carriers onto the other side. So that's called optical injection. And in the diode chapter, the next module, we're going to look at electronic injection of carriers. And then we also talked about the 4 carrier processes. Make sure you know these backwards and forwards: generation, drift, diffusion, and recombination. If you know those 4 things, then I could tell you to look at a new device. If you understand those 4 processes and you have a good idea of energy band diagrams, you could actually give an intuition of how a new device might work. I've given extra credit questions on tests about that. Like one time I gave the energy band diagram of a CCD camera. And I said, like, here's the energy band diagram, explain how this thing works. And a lot of people actually got it. You know, if you understand these basic 4 processes and you understand what energy band diagrams are, you can actually make a lot of smart judgments about semiconductor devices. So the last thing we talked about was a continuity equation. It's basically a conservation of charge, not mass. It's a conservation of charge equation that considers the rates of generation, recombination, drift, and diffusion. So at this point, you should know, I would say, the ABCs of semiconductor devices. The basic building blocks of semiconductor devices. The rest of the modules are going to cover the specific devices themselves. So we'll talk about the diode, we'll talk about the MOSFET, and we should hopefully have enough time to get into the BJTs and optoelectronic devices. But this module and the last module, if you don't understand these 2 modules, you will certainly have difficulty in understanding the next 3. So make sure that you understand these 2 modules quite well. If you have any questions on the homeworks, happy to spend time on that. So are there any questions so far, points of confusion on today's lecture? Okay. All right, good. So we can end there. I'm going to fix this now so I don't forget. And I'll stop this recording.